To this point in the course, we've learned an awful lot about chemical reactions. We've learned what chemical reaction is and what different types of chemical reactions can occur. We've learned how much material could be involved. If we start with a certain amount of reactant, how much product will it make? We've also learned something about the heat that reactions can generate or that they can absorb as they move forward, and to what extent they go to completion. That is, do they stop midway somewhere and form an equilibrium? We've learned about acids and bases. We're now going to tackle a new aspect of chemical reactions, and that is how fast they occur. This is one of my favorite areas of chemistry, and I hope you'll enjoy it as well. But before we can talk much about it, we're going to have to define a few things and talk about how one thinks about speed in the context of a chemical reaction. We're going to have as learning goals how we can define how fast a reaction occurs, and part of that definition is going to involve defining something called the order of a reaction, and we'll talk a little bit about what that means and how we can identify it. So let's get started. When we talk about a reaction, in order to understand something about how fast it occurs, we need to understand how it evolves in time. So as an example, and we're going to be using this throughout this lesson, I want you to consider the reaction of N2O4 breaking into two parts, two NO2 molecules. Now we've seen this reaction a little bit before. It's a great way to characterize equilibrium. The NO2 is brown, the N2O4 is clear. So in some sense we can measure where the equilibrium stands by seeing how brown the sample is. Now when we set this up, let's imagine that we can create a vessel that contains only N2O4 at some instant in time. So our starting point is going to be to have some concentration of N2O4 in our, in our container and 0 NO2 in the container. So what happens now? Well, eventually those molecules are going to bounce around inside the container. They're going to collide with one another. Some of those collisions are going to cause the N2O4s to break apart into two NO2s. So we're going to see that during the course of the reaction, the N2O4 is constantly decreasing. In fact, if you look at the blue line on the graph, that's tracking what the concentration of N2O4 is as a function of time. You can see that it always slopes downward. It never jumps back up again. Now, that's not to say it can't happen in a reaction, but most reactions, the reactants go away in a very smooth manner, as is shown here. What about the NO2? Well, there's no NO2 at the beginning, so the red curve that tracks the time evolution of NO2 during the course of the reaction starts at 0, and it gradually builds up. And we can see that during the course of the reaction, the NO2 constantly increases. All right, well, little mystery about that, because NO2 started at 0, and we know it had to end up somewhere in a positive territory. Both of those reactants, then, as they evolve in time, they begin to flatten out. So one of the things that we can say is that the slope or the steepness of the change in those curves is greatest at the beginning, and we say that's where the rate is the fastest. And then as they approach equilibrium, it slows down. And when it reaches equilibrium, you can see that's the part where both of those graphs, the blue and the red lines, are absolutely flat in the time evolution curve. Okay, once we've reached equilibrium, we no longer see that there's any change happening in the reaction. Now, we do know from our study of equilibrium that there is a dynamic equilibrium occurring. And in that region, some of the N2O4 molecules are still breaking apart to form NO2, but we also have NO2 molecules coming together to form new N2O4. So it's going back and forth in an equal fashion at the same rate. So we say that once the reaction reaches equilibrium, things are not changing anymore. That's another way of saying the rate is 0 when we reach that equilibrium. Now, if we look at a finer scale, we're going to look in the area that's circled by the purple circle. We'll see a close-up of both of those reaction profiles. And we're going to define something called the slope, that is to say the tangent line to each of those curves. And we're going to use that to define something about how fast the change is occurring. And you'll notice in this, I've actually specified that for the change of N2O4, the slope is negative m. Now, why did I write it as negative m? Well, negative implies that the N2O4 is decreasing. so it has a negative slope. And indeed, we know from graphing lines in algebra that a line that starts high and ends low is one that has negative slope. So the m is just a placeholder for whatever that slope happens to be. Now you'll notice below that on the red curve, again we've characterized the slope, and in both cases the slope is the change in the concentration of that reactant divided by some incremental time. But the slope of the NO2 is now a positive, and it's a plus 2m. So why is that 2, whereas the other one was just minus 1m? Well, that's related to the stoichiometry of the reaction. Every time an N2O4 molecule falls apart, it creates 2 NO2 molecules. So the rate at which NO2O4 is declining is always going to be half as great as the rate of NO2 increasing. So we should see, in fact, that the NO2 increases at twice the rate that the N2O4 declines. Now this is also reflected in the gaps between where these two species start and where they end when they get to equilibrium, and that's marked in green on the right side of the graph. You'll notice that the N2O4 starts where that black dashed line runs across, but it ends where the blue line is level. So that gap between the two indicates how much of the N2O4 underwent a reaction. Similarly, if we start with the NO2, we start at the bottom and we end up on the red horizontal line. And so that gap is twice the size of the gap that we saw above. So that simply reflects the stoichiometric ratio of the reaction. Okay, so we've spent a lot of time examining this diagram. Let's get more into the details of what constitutes a chemical rate. So how do we measure speed in life? Well, normally we think of speed as a distance covered per some unit time. That could be meters per second, or if you're driving a car, it could be miles or kilometers per hour. Okay, but it always involves dividing a distance by some time that is spent covering that distance. Now, there are other ways to define speed, and we can define the relative speed of two things by, for example, putting them in a race. So in a human race, the winner is the first runner that crosses the finish line. And that gives us one sort of measure for who is the fastest runner. But I'll remind you that there is an old fable, and you've probably heard it when you were a kid, about the tortoise winning the race against the hare, the rabbit. All right, well, the tortoise clearly wasn't the fastest runner, but they did cover the distance of the race fastest. If instead of defining the winner of a race as the person that crossed the finish line first, what if we define the winner of the race as the one that achieved the highest instantaneous speed during the course of the race? Well, in that case, the rabbit would have certainly won that because it was certainly running faster than the tortoise. It just took time to take a nap and didn't reach the finish line first. But you can imagine how the Olympics would be different if instead of always setting a finish line somewhere, but simply charting everyone and using some kind of electronic gear to measure how fast they were running, we gave the award to the person that actually achieved the highest speed. Well, we don't do that, but it'd be a different way to do the Olympics. So in the case of reactions, we're interested in something that changes over a period of some time. Well, in this case, we're going to be talking about reactions that start with some reactant, A, and go to some products. As it turns out, when we study the rate of reactions, we don't really care what the products are. That may sound funny, but all we're interested in for the most part is the disappearance of reactants. Now, the way we would measure the amount of reactant would be, for example, to measure its concentration as a function of time. So in this case, what's going to be key in our study of reaction rates is to look at how the concentration of our reactant A changes over some period of time. So that's represented mathematically as the rate is equal to negative delta concentration of A over delta T. So the delta concentration A is a change in the concentration of A. The delta T is a change in time. Now you may be wondering about the negative sign. Well, since the reactants are presumably going away and the products are being formed, we're always going to define it this way. So there's that negative sign. I may forget to say the negative sign when I talk about the rate, but for reactants, there's always that negative sign there. It is disappearing during the course of the reaction. Now, let's go back to our N2O4 example, going to 2NO2. So we might characterize a rate law for this process. So what we're interested in is how can we express how this concentration changes with respect to time. Now, I haven't done anything to justify this, but in fact we find in most reactions that we can express this change in concentration over a change in time in a very simple mathematical way. We set it equal to a rate constant, K, times the concentration raised to some power n. All right, so this is going to be you'll see this kind of equation written quite a lot when we talk about chemical kinetics, but it turns out that reactions can be characterized quite successfully this way in terms of defining their rate. All right, so now I'll just remind you again that this change in the concentration over a change in time really represents the slope of these figures, of these time curves as they evolve in time. All right, so we're not talking about something magical or only mathematical. We're really talking about how these things change over a period of time. So it's the slope of these curves. Now this expression that we've written down, negative delta A over delta T is equal to K times the concentration of A raised to the n power, is something that we call the differential rate law. Okay, it's essentially the instantaneous rate of the reaction that's defined by that, because we've already seen that that instantaneous rate changes during the course of reaction. It's fastest at the beginning, it slows down as we approach equilibrium. Now, you may be a little bit put off by the word differential. It refers to calculus, because yes, in effect, what we're basically doing is we're defining a derivative of the concentration with respect to time. Now, I know that not all of you have taken calculus. Maybe some of you never will take calculus. Don't worry. I'm not going to be asking you to take derivatives. I'm simply trying to make connection with you to some other mathematics that someday may be useful for you or maybe not. All right, but we'll just work in terms of small incremental changes in the reactant concentration and small incremental changes in time. Now, here's where we find out something more about that special equation, K times A to the n. That exponent n is something we call the order of the reaction. And I hope that you can appreciate that for different values of n, we may see very different behaviors. For one thing, we characterize the order of a reaction based on the value of n. So when n is equal to 0, we call it a 0th order reaction. When n is equal to 1, we call it a first order reaction. And when n is equal to 2, we call it a second order reaction. Now, theoretically, we could have a third order and a fourth order reaction, and those do occur in nature, but we're going to focus just on these first three because they're by far the most common orders of reaction that we see in kinetics. So we have three possibilities for these rate laws: first, second, and 0th order. We have a reaction rate that's going to be characterized as a change in concentration over some unit time. So the units of our rate, instead of being meters per second, they're going to be something like molarity per second. It's a change in concentration. And it's important that we have those units because they are going to determine for us, what the units of this rate constant K have to be in order for everything to work out right. So here are the various possibilities for the three different rate orders. We have rate is equal to K times A to the 0 power. That's a 0th order reaction, so that's just equal to K. So in other words, the rate, which is in units of molarity per second, is equal to K, so K must be in units of molarity per second. They have to have the same units. When we go to first order reactions, the second equation there, the rate is equal to K times A raised to the first power. So we have K times something that has units of molarity already, and that's going to be equal to the rate, which is in units of molarity per second. So in order for those units to match up, the K has to be in units of 1 over seconds. Okay, so when it multiplies by molarity, we'll have a net unit of molarity per second. It's a little bit more tricky when we get to second order reactions. So there the rate is equal to K times the concentration squared. And in this case, the units of K are going to be multiplied by molarity squared in order to get a final unit of molarity per second. So in this case, the units of K have to be 1 over molarity times seconds for those units to work out. Now, what do these three cases look like? In the case of a zeroth order reaction, we said the rate is equal to K, so it's constant. So if we look at rate as a function of the concentration of the reactant, we see that it's just constant. It doesn't depend on the reactant at all. It stays the same throughout the reaction. This is, of course, going to be different when we look at first and second order reactions. In the case of a first order reaction, the rate is just equal to, or is proportional to, the concentration of the reactant. So that's just a line. Okay, and the slope of the line is basically our rate constant, K. So you can see that the rate is faster when the concentration of A is larger, and it's smaller when the concentration of A is smaller. Now, the reason we think this way, and the reason that this makes sense, is that if there are more reactant molecules around, they're able to react with one another. They're able to undergo the reaction and become product. So it does make sense that the rate would be faster when more A is available. And we saw that in our N2O4 decomposition graph. All right, when we go to second order reactions, we have a steeper rise. The rate is still dependent upon the concentration of the reactant, but now it's going to rise more steeply as the reactant concentration rises. In fact, it's basically the equation of a parabola when the rate is equal to 2. When the order is equal to 2. So in this case, we're going to see a curve that looks something like this. Again, as the concentration of the reactant goes smaller, that rate declines and eventually, of course, would go down to 0 when there is no reactant left. So we've considered a fairly simple reaction which has only one reactant going to products, but we know that most reactions have more than one reactant. So as an example, let's consider the hydrogenation reaction of acetylene. So acetylene is C2H2, reacts with hydrogen gas to form ethane. Now, in this case, we might ask the question, how would we write the rate law? Would we use acetylene or would we use hydrogen? Well, the fact of the matter is we can use either one of them, but we have to pay attention to how those two definitions of the rate law might be defined relative to one another. So if we, for example, use the rate of C2H2 disappearance, we would write that as negative the change in the concentration of acetylene over some change in time. Now, I'm not going to specify what that is, but let's say that X acetylene reacts in that little bit of time, so we might characterize that rate as negative X over delta T. So how does that compare to the rate of H2 disappearance? Well, every time one acetylene reacts, we have two hydrogens that react. So if I were to similarly write a rate expression in terms of the change in the hydrogen molecule concentration over delta T, instead of X, it would be minus 2X. That way, this X is the same in both cases. We're charting the same reaction. So we can relate these two together in an overall rate law by doing the following. If we define the rate to be the rate of disappearance of acetylene in some period of time, delta T, then that's actually going to be disappearing half as fast as the disappearance of the H2, because two H2s disappear every time one C2H2 disappears. So we would write that as delta C2H2 over delta T, negative of that, is equal to negative 1/2 times the change in H2 over change in time. Now, just for completeness, I've also written the rate of appearance of C2H6. Since the other two are disappearing, they're negative, but this one is appearing, so it's positive. And one C2H6 is appearing every time one C2H2 is disappearing. So its rate is going to be related fairly similarly to C2H2. Okay, the 2 clearly comes from the balanced equation coefficients. All right, so the factor of 2 that relates this hydrogen molecule disappearance, the acetylene molecule disappearance, has to come from the balanced equation. So we can look back at our reaction of N2O4 and determine that, in fact, its rate would be characterized as the rate of N2O4 disappearance, but that's got to be equal to 1/2 the rate of NO2 appearance, because every time one N2O4 disappears, 2 NO2s are produced in the reaction. We will rarely be writing our rate laws in terms of products. In fact, it almost never happens that way. We almost always write our rate laws in terms of the disappearance of reactants. So now that we have some of the machinery in place, we want to consider a general rate law. If we have two reactants, and I'll just call them A and B, and they're going to products, and once again, I don't really care what the products are because I'm going to use the reactants to define the rate. I can write a general rate law now that sets the rate equal to a rate constant K times the concentration of A raised to some power and the concentration of B raised to some power. Now, this may seem very abstract, but in fact what we're going to find is that we can learn what those powers of A and B are by analyzing data, and we can also use that data to find K, and that's something we'll talk about later in this module. All right, for now I want you to just get that equation in your head as something that we're going to be learning how to define that equation better simply through an equation analysis. But as an example of this general rate law, if we want to look at, for example, the synthesis of ammonia from nitrogen and hydrogen gas, some of you may remember this is the Haber process for production of ammonia. We would write that general rate law in terms of the concentrations of N2 and H2, N2 raised to 1 power, H2 raised to a power as well. The two powers could be the same, they could be different, doesn't matter, and they will have a rate constant. I should note that the rate law almost never depends on the products. It does on very rare and weird, unusual circumstances, but for the most part we're going to have rate laws that depend upon the concentrations of the reactants. So you might ask, are the exponents that I've drawn here, M and N, are they related to the coefficients in the balanced equation? It's a question that probably occurs to most students as they're studying chemistry. And the answer simply is sometimes, but not always. In fact, those two coefficients, those two exponents, are not related at all to the balanced coefficients of the balanced equation. So they're something that we have to find experimentally. We can't just automatically write them down. Now we will see in a later lesson an instance of a particular type of reaction where we can make that assumption, and that's why sometimes it is true. But for most part, we can't just assume that the balanced equation coefficients are the same as the exponents in the rate law. So I hope we've learned a little bit about how we define how fast a reaction occurs, and of course what an order of a reaction means. It says something about how the rate changes as the concentration of a reactant changes. Thank you.